Welcome to SAEC YouTube channel featuring GATE. I'm Dr.S.KAMALAKKANNAN, Department of EEE, accredited by NBA at SA Engineering College, accredited by NAC with A grade. Thought sharing, knowledge becomes a power only when we apply it with a purpose. Right. So this is the GATE syllabus, right? So in this I'm going to focus on electric machines, in particular electromechanical energy conversion principles. Fine. So these are all the contents of my presentation. So here I'm going to talk about the principle in the sense I'm going to talk about the motor principle, okay, where the force will be produced, then generator principle where the EMF will be induced. The next is what about the storage of energy in a magnetic field, then how come the force and torque are produced from the magnetic field stored energy. Then we'll be talking about energy balance equation, then energy conversion in electrical machines, then conditions for energy conversion. Last but one will be types of electromechanical converters, and the last but not the least will be the applications and conclusions. Fine. So what is electromechanical energy conversion principle? It's process of converting one form of energy to another form of energy. If you take motors, will be converting electrical energy to mechanical energy, whereas in generator will be converting mechanical energy into electrical energy. Right. So in a nutshell, what is electromechanical energy conversion? It's nothing but exchange of electrical and mechanical energy, where the device is not going to create the energy, but it is going to simply transfer the energy from one form to another form, which will be between electrical and mechanical domains. So this happens through a very important domain called as the magnetic field domain, right? So this conversion is governed by means of a very important principle called as electromagnetic principle, and it is nothing but the interaction between two fields, right? That is, one is nothing but electric fields and magnetic fields. In addition to that, the mechanical motion also, right? So where this occurs, that is very important, this occurs in motors, right? Then generators, third in relays, fourth solenoids, and finally at actuators, right? So the medium of conversion, okay, if you take magnetic field will be the medium of conversion, okay, which will be dominant when compared to that of the electric field. Electric field will be less dominant, okay, that will be minor, right? Whereas the magnetic field will be major, right? So what is the basic principle? Yes, so energy conversion is a topic here. Okay, how it happens? It happens because of interaction between electrical system, magnetic system, and then mechanical system. Right. So what is electrical system? Electrical system involves a voltage current, magnetic system involves flex field energy, then the mechanical system involves a force, torque, and then motion, right? So the key idea behind this topic will be is the conversion of electrical input into mechanical output, where the medium of transfer will be magnetic field. So that is nothing but motor, right? Then vice versa will take place in generator, okay? But in both the cases, the medium will be magnetic field. That is a basic principle of the presentation, right? So let me talk about the motor principle. Okay, so as told in the previous slide, okay, motor principle is what means output will be mechanical energy, right? So here I'm going to put a conductor which is having a current in it in a magnetic field. When I put a conductor which is carrying a current in a magnetic field, obviously force will be produced. So that force here is F, which is nothing but B into I into L, right? So what is this F? F is nothing but the force, which is otherwise called as magnetic force. Unit will be Newton. Then B is a magnetic flux density. Unit will be Tesla. I is current in the conductor. Unit is amps. And L will be effective length of the conductor inside the magnetic field, and unit for it will be meter. So this principle will be describing the magnetic force which will be experienced by the conductor carrying the current which has been placed in the magnetic field, right? So here I am taking a two conductors, that is, one is nothing but a straight conductor, okay, and the other is nothing but a conductor in a coil. So in a straight conductor, what happens is, example for straight conductor will be actuators, okay, that will be producing linear motion in response to that of the input given, which is nothing but electrical signal. So this will be producing the linear force, right? Then if you take the conductor in a coil, okay, as in case of the motors, it will be producing the force or the torque, okay. So here to put it in a simple sentence, a straight conductor means going to produce linear force. Then if it is a conductor in a coil, it will be producing torque, okay. So where it is applied, that is very important. It is applied in case of DC motors, AC motors like induction motors, synchronous motors, and finally linear actuators, right? So that is the principle of motor. Then what is the principle of generator? So here we are going to induce the EMF, right? So when I am taking a conductor and I am moving a conductor in a magnetic field, what will be the EMF induced means is E, which is nothing but B into L into V. So here E is nothing but induced EMF, which will be in terms of volts. Then capital B will be magnetic flux density, which will be in terms of Tesla. L, effective length of the conductor, which will be in terms of meters, and V, velocity of the conductor, which will be perpendicular to the magnetic field, unit being a meter per second, right? So yes, the Faraday's law. Okay, so what Faraday's law says is whenever a conductor, right, cuts a magnetic flux, an EMF will be induced in it, right? So as per this principle, E is minus N into d phi by dt. Okay, so this is induction of EMF. Then how the direction of induced EMF is obtained, that is very important. So that is by the scientist Fleming. Okay, so he had framed two rules. Here we are using Fleming's right hand rule. So thumb will indicate motion, forefinger will indicate magnetic field, and middle finger will be indicating the induced EMF. So these are all basis for all generators and alternators, right? So this is the magnetic field storage of energy, how the energy is stored in magnetic field. As I already told, the field is going to be common in both the cases, whatever it may be, the field is going to be common, okay, which is dominant here, okay. So I'm going to store the energy in the magnetic field, right? Okay, what happens here is the current is going to flow through a coil in the sense here it is inductor, okay. When the current is flowing through the inductor, which is nothing but a coil, is going to create a magnetic field, right? So obviously what will happen means energy will be stored in the field, okay. So that is actually called as field energy. Since the energy is stored in a field, it is actually called as field energy, right? Here one point is very important, energy is stored in the magnetic field, not in the conductor itself, okay. So the energy which has been stored in the field is very important when compared to that of the energy stored in the conductor, right? Then what is the energy stored is what is the amount of energy stored in the field is the amount of energy stored in the field is indicated by means of WF, okay. So the formula being 1 by 2 L into I square. So here WF is field energy, F stands for field here, okay, which will be in terms of joules, L inductance of the coil, okay, which will be in terms of Henry, and I current flowing through the inductor, which will be in terms of amperes. So it is very clear that the field energy is proportional to inductance L, okay, and proportional to square of the current, okay. So what are the key insights from this formula is the first key insight is energy is depending only on the current and not on the voltage, okay. Then next insight is what means is when you increase the value of current I here, what will happen means the energy which will be stored in the field will also increase, okay, as both are proportional to each other, okay. Finally, what is the insight means the energy which is present resides in the field space, not in the conductor. That is a very important insight, right? So then comes the co-energy. Co-energy will be along with the field energy, okay. So this co-energy is a physical energy. It is a complementary energy function which has been derived from the energy which has been stored in the magnetic field, which is nothing but the field energy. So what is the purpose of this co-energy? Is the co-energy is used to derive the force as well as the torque. Okay, so once the force and torque are derived, okay, we can proceed with the devices under consideration. For example, the motor, right? So this is what the energy. Okay, so we had seen two energies here. That is, one is nothing but field energy, which has been stored in the field itself. Okay, and another energy is nothing but co-energy, which will be associated with the field energy. And the last point that is very important is especially useful when flux current relationships are non-linear. So when co-energy plays very important role is, of course, co-energy plays very important role when the flux as well as current are not linear. Okay, in that case the co-energy will be playing a important role in addition to that of calculation of force as well as torque, right? Yes, so here I'm going to talk about the force as well as the torque. So I had stored the energy in the field, not in the conductor. I had stored the energy in the field. Okay, from stored energy I'm going to obtain my force as well as the torque. So how it is obtained, that is very important. So force, okay, what is force here means? Yes, F is the force. Okay, so I had taken linear motion here. So F is rate of change of field energy with respect to that of the position. Okay, yes, F is here energy which has been stored in the field, and X is the position. So when I do rate of change of field energy with respect to that of the position, I'll be getting the force, right? Then how to get the torque? Yes, in the same way, what I should do here means, yes, I have to differentiate the field energy with respect to that of the angle. In the previous case, I had taken the position, but here I am taking the angle. So when I'll be getting the torque means when I partially differentiate the field energy with respect to that of the angle, I'll be getting the torque. So what's the difference between the two? Yes, in both the cases, right, force as well as torque, what we are going to do means, yes, we are going to differentiate field energy only, but with respect to that of what? In the first case, with respect to that of the position. In the second case, with respect to that of the angle. Okay, so this WF as indicated in the previous slide has been calculated as what? Half into L into I square. So to put it in simple points, what is this force or torque means is how the co-energy changes with respect to that of the displacement, that is nothing but X, and then the angle theta. So this last 2 points are very important. Is what is this force? When the force appears? Yes, the force appears when the co-energy changes with the position X. Okay, what is the inference from that means is if moving the armature increases co-energy, the system will be producing the pulling force. That is the inference. Okay, then next is a torque. Okay, what happens with the torque? Yes, when the torque appears, yes, when the co-energy changes with respect to that of the angle theta. Okay, so here also, okay, what happens if you rotate the rotor means here also the co-energy will increase, but here the system will be producing the torque. So the first case, what I am doing means is the system is going to produce pulling force. In the second case, the system is going to produce the torque. Okay, why means is I am differentiating the co-energy with respect to that of the position X, but here I am differentiating the co-energy with respect to that of the angle theta, right? That's why
torque in the second case
and pulling force the first case, right? Right. What is this energy balance equation? So energy balance equation, what is the expression here means yes, it is a relation connecting input, output, and then losses, right? So he had taken electrical input energy. Okay, input here means what? Electrical input energy. And then output in the sense what? Mechanical output energy. Okay, it has to be added with what? The energy which has been stored in the field. Okay, so what is the formula? Electrical input energy is equal to what? Increase in stored energy plus mechanical output energy. So here this energy balance equation, okay, what is this energy balance equation shows means is the input electrical energy has been split into different parts. What are they means? The first one is a magnetic field energy, which is a temporary one. Okay, next is what? The mechanical energy. I told that it is output. So a very important thing is it is useful output. So along with that, we'll be having losses also. Okay, is losses in the sense what? I cannot avoid the losses. Okay, yes, that's why I had given the word unavoidable losses. So what are the losses here means? Yes, I square R loss, which is nothing but copper losses. Then the second one is core losses, right? Core loss includes what? Eddy current losses and then hysteresis losses. Then the third one is mechanical losses, which includes a friction as well as a windage, right? So this will be the basis for what? All machines such as motors and generators and other devices such as solenoids and then actuators. So conclusion for this slide will be what means I cannot create the energy, I cannot destroy the energy, but I can transfer the energy, okay, from one form to another form, which is nothing but a law of conservation of energy. So here I am transforming between what means electric, magnetic and mechanical forms. Here, as mentioned earlier, magnetic will be the major domain, okay, in both the cases, right? So this is the illustration, diagrammatical illustration, okay. So if you take the motor mode, what happens there is the input is electrical and output is mechanical. If you take a generator, the input is mechanical, output is electrical. As mentioned earlier, see in both the cases the medium is what? Magnetic, right? So in motor mode, what all the parameters will be taken into account is that is the parameters will be voltage and current that is going to create the magnetic field, right? Then here what happens means the field will be interacting with the rotor, okay. So when the field interacts with the rotor, what happens is rotation will be produced, and then before that the torque will be produced, and then the rotor will be rotating here. That is motor mode. Then what about generator mode is so prime mover.
Rotor will be driven by means of prime mover.
Okay, so as a result of that, I mean what will happen means there will be a change in flux. The change in flux as per the law mentioned earlier, okay, change in flux will be inducing the EMF, and ultimately the power will be delivered to the load which has been connected the output side. Then what all the subsystem involved here is you have electrical subsystem, magnetic subsystem and mechanical subsystem. So electrical subsystem includes windings, okay, it will be including windings, okay. Then what all the parameters means voltage and current, okay. So here current will be flowing, okay, EMF will be generated, losses will be incurring in electrical subsystem, right? Then what about magnetic subsystem? Magnetic subsystem will be including core, air gap and then flux path. So here energy will be stored. That energy is actually field energy, okay. Along with that field energy, we'll be having the co-energy. Then the mechanical subsystem. So mechanical subsystem will be having what is? It will be having a rotor, shaft, right, bearings, and then the load which has been connected the output side. So what the mechanical subsystem actually do here means is it is going to produce a torque and then the speed will be produced here, okay. That's it, right? So this is the subsystem involved here, okay. Then what is the condition for energy conversion? Okay, so right, fine, we had developed the energy, okay, we had seen the principles, right, motor principles, generator principles, then we had developed the energy, then we had differentiated the energy, okay. So we had developed the force, torque, everything, right? What is the condition for this energy conversion? Yes, sir, I had taken into account some 4 conditions, right? I had to set some conditions. It may be what? Physical and operating conditions. So that will be ensuring the machine running, right? So that will be ensuring the conversion, proper conversion of energy, right? Right. The first point is very valid, okay. Yes, what it is means without magnetic field, I told in the beginning itself, okay, in both the cases magnetic field is going to play a dominant role, I told, right? It is a medium, I told, right? So if there is no magnetic field, what will happen, right? Yes, no torque, no EMF. No torque means what is that will happen in motor. No EMF means what? That will happen in generator. So the field is very important, okay. That field will be producing the flux, imaginary flux, right? The second point is also very important, is that is motion between what it is a field as well as conductor. If there is no motion, there is no energy conversion at all, okay. There is no motor, there is no generator. Then the third one, that is a proper conducting paths for current are induced EMF. Yes, the current has to flow through a proper path, that is very important. Then only EMF will be induced, right? Then a strong magnetic coupling between electrical and then mechanical paths, right? Is a coupling, very important. It is actually called as magnetic coupling, okay. So if you have proper magnetic coupling, only energy will be properly transferred, okay. Right. Then what are the types of electromechanical converters? If you take rotating machines, you have DC machines as well as AC machines, right? DC machines is given there. Then AC machines, in the sense what induction motors and synchronous machines. Then I can also proceed with the linear devices. Linear devices, I told okay in the beginning itself is very best example is what linear motors and then solenoids. Then reluctant devices also I can take, which is nothing but relays and then stepper motors, right? So these are all the few types of electromechanical converters, which is applying the principle what we are discussing, right? So what are the applications and then conclusion? Application is very important for any topic. Application and conclusion is very important. Where I am applying this is if I take industries, I'll be applying this in motors, pumps and then conveyors. Then in power station, I mean power generation, okay, in alternators and wind turbines. Then home appliances, fans, right, mixers, right, refrigerators. Then in automation, I'll be using in robotics and actuators. Then automotive, if you take, I'll be using in electric vehicle motors, EV motors, alternators, right? Fine. So to put it in a very simple sentence is we have taken the energy conversion, okay, that is electrical to mechanical or mechanical to electrical, okay. So the bridge between these two will be what means the field. That field is actually called as a magnetic field, okay. So we have taken another one important here is that is how to calculate the force as well as torque, okay. How the force as well as torque is calculated means with the help of the energy which has been stored in the field, right? That is nothing but field energy. Along with that, you'll have the co-energy also. That co-energy has been taken, and then we had derived the force equation as well as a torque equation. Okay, so this is very important. This will be the heart for any electrical machines, right? So to put it in simple sentence, I have taken the principles, right? Principles in the sense, I have taken motor principles, then I have taken generator principles, right? Then I have taken the energy which has been stored in the field, which is nothing but field energy, right? That is nothing but half into L into I square. What are the insights there means is energy is proportional to what is the square of the current. Okay, then L will be what? It is actually the inductance, right? So after storing the energy, after developing the field energy, I have taken into account the co-energy also. Co-energy will be along with the field energy, that also I have taken into account, right? So that co-energy is only used for obtaining the force as well as torque formulae, right? So that has been explained, that has been given as a formula, right? That energy which has been stored and then the force as well as torque which has been developed has been used for all the machines. Okay, that is the simple insight of all these PPTs, right? We will see some gate questions which has been asked in the previous years, right? So this is a question asked in 2014, gate EE 2014, right? This is gate previous year questions in the topic electromagnetic energy conversion. Yes, what is this? In an electromechanical energy conversion device, any device, right? I had given many examples, but this was very specific. Yes, how the energy conversion occurs? What is the interaction between? That is the question asked here. So what are the options given here means A is voltage and current, B is flux and current, C is speed and inertia, and D is what? Resistance and inductance. Yes, as we discussed, okay, the correct option will be B, which is nothing but flux and current. Why? See, when the flux interact with the current only, what will happen means torque or the EMF will be produced. Okay, you cannot proceed with the other options. Other options will not help to produce the torque or EMF, right? Only the flux, right, along with the current will be interacting and then will be producing the torque or EMF, right? So this is a question asked in gate EE 2014. In the year 2014, this question has been asked. A simple question it is. We'll see another question is. So this is a very nice question. Okay, problematic it is. It has been asked in the year 2017. Gate EE 2017. So what is the question? A relay has a magnetic force given by expression for force is given F is equal to K into I square by X square, where I is equal to current, X is what? Air gap length, right? If current is doubled and gap is halved, this is a condition given the problem. What happens to force, right? So once again, so what is force? Force is nothing but K into I square by X square. Then current is defined here as I. Then air gap length is defined as X. One condition is given, okay. So what is that condition? Means current is doubled. And what about the gap? A gap is halved, right? So in this situation, what is the force? That was the question here. Right. What is the original force given the problem is the force originally given the problem is K into I square by X square, right? So here, what is the new current? Current has been doubled. So actual current is high. New current is what? 2I. Why? The current is double here. Then gap is halved. What is the meaning for halved? Means 1 by 2. What is the gap here? Is gap has been defined, air gap has been defined, it is X. So X by 2 it is, right? So substituting this new current as well as new gap in the force equation, what will be getting is a K times of, in place of current, you substitute the new current, that is nothing but 2I. Okay, current is squared, so 2I the whole square. Whole divided by, okay, in place of X, you substitute the new gap. Gap is halved here, so you'll get what? X by 2 the whole square, right? After substitution, what will be getting means 4K I square divided by X square by 4. Right? So which is nothing but what? 4 into 4 times of K I square by X square. So what is this 4K I square by X square? Is that is what is this K I square by X square? That is the actual force given. So that actual force is what? Fn. So this can be called as Fn. So 4 into 4 will be 16. So what happens? Yes, now the force increases by 16 times. Inference is very, very important. See, when the current is doubled, okay, I'm making my current 2 times, okay, and when the gap is halved, okay, what is the meaning for gap is halved? Means air gap is 1 by 2 now, right? So what happens when all these changes takes place? Means force will be increases by 16 times, right? That is the inference of this problem. Okay, what was the question? What happens to force if current is double and gap is halved, right? Yes, when current is double and gap is halved, my force will increase by 16 times of the actual, right? So this is a question which has been asked in the GATE EE 2017, right? What is the next question? Yes, the energy balance of electromechanical system includes which of the following? So this is a question which has been asked in the GATE EE 2018, right? So option A is what? Electrical input. Option B is what? Mechanical output. Option C is what? Stored field energy. Option D is losses. So obviously, yes, for balancing the energy in electromechanical system, okay, you have to take all the 4. You need electrical input, right? You need the mechanical output, and third one, very important one, the energy which has been stored in the field called as stored field energy, and along with that, losses will also come into account. So the correct answer will be what? All the 4 options, right? That is nothing but electrical input, mechanical output, stored field energy, and losses, right? So to put it in very simple words, right, I have taken the energy conversion, okay, how the energy conversion takes place, right, how the force is developed, how the torque is developed, right, before developing the force and torque, how the energy is stored, right. So all those things are taken into account. Based on that, we had seen some previous year questions. This is asked in GATE EE 2022. The torque in a rotating machine is given by T equal to d by d theta of WE. If the magnetic co-energy varies as WE is equal to 5 plus 2 cos theta, find torque at theta equal to 90 degree. So this is also a very nice question which has been asked in GATE EE 2022. So what is this question about? Is torque is given, which is nothing but d by d theta of WE, right? So is again this is the energy with a different notation. Okay. So if the magnetic co-energy varies, the energy co-energy is going to vary. How it is going to vary means WE is equal to 5 plus 2 times of cos theta. When it varies, find torque. Okay, yes, they are given the angle also. What does that angle means? 90 degree, right? So the torque given in the problem is what? D by d theta of WE. WE is also given the problem. Substitute WE in d by d theta. So I'll get what? Torque is equal to d by d theta of 5 plus 2 cos theta, right? So obviously you have to differentiate this with respect to what? D theta. So I'll be getting what? Minus 2 times of sin theta. But what is the question asked? They didn't ask simply the torque. They had asked the torque at theta equal to 90 degree, right? So at theta equal to 90 degree, what I should do means is I have to substitute theta as 90 in the above equation. So I'll be getting what? T equal to minus 2 times of is I had to substitute sin 90. Sin 90 is nothing but 1. So I'll get what? Minus 2 Newton meter, right? So this is the torque at theta equal to 90 degree, right? So what was given the problem? T is given the problem. What was asked in the problem is what is the condition given the problem? Is the co-energy is going to vary, right? In that situation, what about the torque at theta equal to 90 degree was the question, right? So I had taken the torque, okay, then I had differentiated what it is the energy with respect to that of theta. Y means that is the formula for torque, okay. So I had substituted WE, which has been given the problem. I had differentiated that. Then question asks is what? Not simply torque. If it is simply torque, I can leave here itself minus 2 sin theta. But here question is what? Means a torque at theta equal to 90 degree. Substitute theta equal to 90 degree. So we'll get what? Minus 2 times of sin 90, which is nothing but minus 2 Newton meter. Okay. So this will be the electromechanical energy conversion principles, and then a few problems are based on that electromechanical energy conversion principles. So again, this will be continued in the next series. So before closing, okay, thank you for your time. Let's turn today's ideas into tomorrow's impact. Okay, so it's a very big area. I had taken only a nutshell of that. I had taken only a drop in the ocean. Okay, so we have to further explore it, right? So that is turning what today's ideas into tomorrow's impact. Thank you. I'll be continuing in the next video. Thank you.